So Eric made a great description before about, you know, the theory and some of the mathematics and so on. And I try to make, I like to make things simple, okay? So just briefly, a neural network is a number of perceptrons or neutrons that take a value that comes into a neural network, okay? These things are distributed through a number of layers. So they activate and is sent down to these layers. There are weights that are multiplied by the incoming signals, then added and then sent along, in this case to this output layer. The neural network I'm using here is just like this one, okay? You will see that in the code in a few seconds. So it's actually that simple. You don't have to make it more complex than that. You can talk about it for hours, you know, but it's that simple. When we're talking about machine learning, not AI, machine learning. All right. Now, one of the things that I've learned, I've made maybe 6 attempts to taking data into a neural network and make some sense out of it and get some output that I want. When I fail, I tend to use a lot of input data that I don't really know what it is or it's arbitrary, and I put it in a rather big network. And then I try to get something out from there. Sometimes I get some data out in the output layer that actually makes sense, but most of the time it doesn't make sense, or at some case it doesn't really give what I want. And then I try to change the input data a little bit, but usually I go into the number of iterations, the learning rate, and I continue and change and change and change, and I never get to my actual goal of detecting something valuable. So I have learned from this that it's much better to use smaller neural networks that just makes one thing. Not putting in, like, you know, GPS positions, elevations, if the sun was up or not, if I were tired or not, and so on and so on. Because in the end, you might actually not get out what you want. Now, if you boil this down, and this is something they talk about a little bit in this business, if you boil this down to small models that you save so you don't have to train them all the time, and then you chain them instead. So for instance, the idea here, my vision is to first detect these elevation types. At the next step, I also want to record the accelerometer to see how I am running, if I'm running steadily, or if I actually have to move around a lot, because then probably there are obstacles, or it's a harder surface that I'm running on. That will be a different network. And then maybe I'll have a third and a fourth. And then I will connect them together to a higher neural network that can tell me whether, you know, I'm tired because I'm running for a long time. You're running on asphalt. You're not usually doing that. And then maybe also get that back to me and say, you know, you should take it easy now because you've been running too far, you're too tired, you don't have a good running technique. That's the vision. Now let's take a look at some code. I have here, I've tried to make as little code changes as possible because I think some here has the experience now that if you need to do a lot of coding here, it's just going to take time. So I have prepared code, just like food. I'm using the same library that I was using in Edinburgh called Synaptic. It's a JavaScript library. It can handle deep neural networks as well, but this is a simple one-layer network. Just to make you understand what you really need is basically, I'm doing this in nodes. You need to install Node, and then you need to install the Synaptic library, and then you're off to do something, okay? This is just some declarations, which the things are we need. Here, I'm defining the neural network. I'm not going to say much about it, but I have chosen 10 input values. Those 10 input values is actually 10 track points during the way. In the end, you will see when I simulate this that I will take 10 track points and then add one, put one out, and then go on and segment all my run like this, okay? And then at each 10 track points, make an assumption, a detection of the running type I'm doing. Not going to explain all the code here, but basically, we come down to numbers. Okay, I want to train my network now, and I'm thinking, okay, so what happens when I run uphill? I'm having some sort of delta values, some sort of 1 meter uphill, 1 meter uphill, 2 meters uphill. These may change, of course, but this is something I call a slow ascent, okay, slow uphill. I also have to tell the network something that's, you know, what do I expect when there is no uphill? Okay, I expect that to be a 0. I expect this one to be a 1. This is then, yes, it's an uphill. This is no, this is not an uphill, okay? Very, very simple. Then this is trained. We have 40,000 iterations. I've come to a conclusion this is a good number of iterations. Learning rate, some other things I'm not going to tell you about. And in the end of this code, I'm just activating this vector exactly like the one we were training, and then this one exactly like the one we were training, just to show you how it has actually learned this. So, this is not magic or anything, but basically here now we have teach the network to understand that this vector uphill is detected correctly. It's close to 1, which means that it's probably an uphill running. And when it's not an uphill running, we also detect that, okay, this is not an uphill running. Simply, okay? Now, if I activate this network with some other information, like for instance, what happens if I take a vector like this, because now we've trained it, so now I can test my network with different kinds of running situations, all right? So I will activate, you usually call that activate, downhill running, slow downhill running, and I will also activate something I call a bumpy road. All right? As you can see now, these things react differently from what I was expecting, because I've never actually taught this network enough for it to understand. Oh, better? Yes. So, okay, slow descent over here. Yeah, I was getting. So, slow descent. Obviously, it detects like, no, this cannot be a slow ascent. We are not going uphill, this was a downhill. These three here are actually vectors that I'm running that actually has other values than the original value. So they are a little bit different, but they are still detecting as slow ascents. This one a little bit less maybe. And then we have the bumpy road. Oh, it's actually detected as a slow ascent. Now, I don't want that. So now we come into, and some of us went to the Scrum course. I'm doing something, now I'm inspecting this, and now I will have to adapt my neural network. So I don't want him to understand that the bumpy road will be a slow ascent. So I have to teach them that. Go back to my code, and I will actually tell him that a bumpy road vector should actually output 0. I don't want him to assume this is a slow ascent, all right? Let me see if I forgot to change something. Okay, and as you can see now I trained the network to actually expect that the bumpy road is definitely not a slow ascent. Okay, so this is how I go about constructing a very, very, very simple neural network, and then I actually inspect and adapt all the time to make it know the things that I want. And I don't aim to do very much data into it. Because that can actually, I've spent sometimes several days trying to make sense of the data that comes in if I'm using too much data. This here takes just minutes to do. And you should also probably not try to do too much. That's my experience. Now, I will just briefly show you, because now I want him to detect more categories. You remember I said this from the beginning, I wanted to detect maybe several types of ascent, descent, and maybe hard ascent and so on. This is just a different file, so prepared here. This here now has 3 categories. So that means that I've added not just one output layer, you have 2 there, now I have 3 output layers here. So I have 3 different categories that I can detect, okay? And obviously I put in all the training vectors to detect different things. We have the slow ascent, which is the first category. We have the high ascent, which is the middle category. That's maybe 2, 3, 4 meters per track point that I'm categorizing as a high ascent. And then we have the slow descent, going downwards, the third category. And then I test it with some different values down here. And this is also vectors that I've come up with. So I take the original vector, I change them a little bit just to see how they react, to test the network. And testing neural networks, I think, in the future will be one key market that we may want to think about. Slow descent, expected to recognize it right there. We have one here as well. We have 3 slow ascents that are quite different. We can see that this one is, slow ascent, but a little bit hard ascent, a little bit higher somewhere. And so on. I also have like expected steady slow ascent, but very minor. And you can see that it's the result that I would expect, Maybe I wouldn't say that this is a slow ascent then, but, this is actually the nature of neural networks. The fuzzy logic that it can detect something that maybe is not exactly like we think it is. So, now this has only been like, numbers that I've come up with. Now, this talk was to be about real data, okay? I was hoping to be able to use the information that we had now running until very late yesterday, 1:30, when you were having fun. I actually got this working. I'm very happy for that. So I'm going to use part of this information that we were running yesterday and take this. Now the numbers will be slightly different because the ascents will be like 0.3 instead of 1 and so on. But I actually trained that on another track in Romelåsen in Sweden. So I'm using train data from a different track, but on this reference GPS route here. Did that make sense? So the difference now then, of course, is that now there's a lot of things that needs to happen. I need to export the GPS data, which I'm doing from here. I can go into Strava. I can do an export GPS, and then I'll get all of the data exported from this run here in Palma. From there on, I'll actually import that into something called ads. This is like a GPS editor. And what I can do in here is that I can actually go in and mark something. And in this case, actually, over here, we had a really hard uphill running. And I can then mark a few points here and export that. Like in this case, 13 points. I choose 10, of course. And I use that as reference data to teach him that this is a hard climb, okay? And this is then what I export and I put in my project and I read the file and I pass the file. I'm not going to show you how. You can Google it or look at my code. So this is what I'm doing. And in the end, of course, I am then exporting a larger GPS tracks to actually run this data on, all right?
Question.
Yes.
Vad tror du att du får för output?
Du menar att
om du har markerat lilla biten av vägen och du säger till den att den här biten den är kraftigt stigande.
Ja.
Men när du springer där så uppfattar den dig som fallande ändå.
Du menar the neural, you mean the neural network?
Yes.
That it would, yeah. Well, that's why I'm testing, okay? So, and obviously there will be situations where you're not getting the expected result. But my experience, as I said before, is that if you try to do too much, then these things start to happen, okay? In this case, it's actually rather clear. It's rather easy to define a ascent or a descent. But obviously what happens is that when you reach the hilltop, then there will be 10 track points where 5 of them will be still ascending and 5 of them will be a little bit, level running. But it doesn't look as bad as you think, really. I mean, you can see how it changes and goes a little bit up and down. And then what you can do, as I said, the higher neural network, then you use that one to actually abstract away these changes. And probably you need some AI code in the end that really, makes some real hard decisions. Anyway, so I'm using exactly the same code, but I'm doing some old school, not ECMAScript 6 stuff, 4 loops here. Just trying to, import and parse things. I just had to tell that. Sorry. And in then here, I also read a reference track called P3, Palma 3, which is a longer route that I then can test my data on. I have chosen also to integrate this with binocular. The reason why I do that is that this small GPS here is the core of everything that I'm doing here. I use this one when I'm running. So this one actually tracks my, not this one though, but usually I do that. So that means that I can actually live get these detections of what happens when I'm running, okay? So that is why I actually send this data that I have from the file to Binocular, and then I can show this on the map. All right. Let's run this code and hope that everything is running as possible. Right. Now, as you can see here now, we train the network with some different types of vectors, but it's the same idea that I had before. I do test them a little bit before I go, so I have some test data to see that this really works. And then I start to segment my run. 10 points, and then this is slow uphill running. Move 1 point, this is slow uphill running. And then I keep running and moving around my GPS tracks. At this minute, we are running just before we discovered this hard ascent. It wasn't a nice, well, actually, I love those hard hills with, there is no trail or anything. That's nice. I will show you. And here, give me just about 20 seconds and it will zoom in on our track. Okay, so you should recognize yourself. You can see the map over Palma or south of Palma. Our hotel is down here. We are currently running here at something that I thought was going to be a street all the way, but it very quickly turned over to some muddy streets, something. I don't really know exactly. And we are actually closing to this point here where it will be steeper. I will show you a picture later. Don't mind these things, these are not correct at the moment. But what happens here now, as you can see, is that it was really timing. Now we go from slow uphill to hard uphill. So it actually detects that now it's not as easy anymore. We are going steep up. I will show you the satellite picture right here. We'll zoom in a little bit. I wasn't expecting that when we looked at it in the beginning, but it was nice. It actually did look something like this. That was the uphill we were running. So obviously then that is detected as a hard uphill running. Now believe me, we had it harder than this. So looking now at the real data and looking at how hard I thought it was to run up and looking at the track and everything, I would actually want to go back and change my training set, because I think that I would like to actually say that to lower the value for when it gets hard to run up. And then when we're getting to the point in the highest point, then it will go over to actually be slow uphill running and actually in the end slow downhill running. We'll see if we actually get to that point. That's all I wanted to show you. And the idea of all this was to show you how I'm taking some data that I come up with. I think about a real case. I train some network and do some prototype testing. Then I move over and I bring in the real data from the trail running. I train that and I test it. And in this case, then I start to integrate it with the data that I actually have. And in this case now it's running live. So if I were using this, at this case right now, this would work exactly the same. The next phase for me here would actually be to make him detect more things. The second phase for me will be to detect accelerometer changes. The third thing may be the weather. The fourth thing may be how far I actually did run. Because I want to detect, for instance, how hard my legs hit the ground, because that will actually hurt me after a while. And I want him to tell me that now you should walk or you should take it easy. I make these mistakes over and over again when I have long distance runs where I want more than maybe my body can make. So, okay, thank you.
Good.
Was it too fast?
No, that's good.
Yes.
Maybe you want to go first.
Sorry?
No, it's okay.
No?
So you have you run a track, so you have your own data, and I'm just saying this if I understood it correctly, just to validate. So you run a track, so you have the data, and there is another data which is more optimal. So you are trying to check if your pace is as it is supposed to be. Is that correct? Is that your ultimate task that you're trying to solve here?
Well, I'm trying to solve because when you're a beginner in everything you do, actually, whether it's hang gliding or running or whatever, it's always hard to learn and to understand, when you should take it more easy. Or mainly in running, I think that many people just run. They don't think much about the running technique and how hard you hit the ground and how you lean your body and stuff like that. If you do it wrong, you're going to hurt your knees. Even if you're good trained, you're going to hurt your knees after 20 or 30 or 40 kilometers. And these things can be detected with, if you mount the accelerometers on the shoes, these actually exist already, you can feel how hard you're hitting the ground. These things might, of course, be different reasons. It might be because you've already run 40 Ks, or it might be because you're running on asphalt. By the way, this was much on asphalt. This is the first time in 3 years I've been running this much asphalt, so I'm pretty happy I made it. But these are the things that you can detect. And my idea is that it will be like a trail assistant. So it will tell you live that now you should slow down because you're running on asphalt, you don't usually do that, or now you should lean forward a little bit more, or whatever. So it will be like a help live when you're running, obviously in your ear, obviously talking to you. Yeah.
So, more specific question, if you can go back to your code where you define the number of hidden layers.
Yes.
How do you decide what should be the number of hidden layers?
The number of middle layers?
Yes.
Well, in this case, Sorry, what did you say the last?
Why is 50?
Yeah, that's a good question. Trial and error for me, at least. It's a little bit about how much data you're putting in there. So I've sometimes tried to up this one to like 200 or 300 and thinking that's got to be better, But in the end, when you do the training sets and when you're looking at the results that you're getting, sometimes increasing that might actually get worse values out, because things might be wrongly detected. And I think if you're thinking about how neural networks works, that might mean that, because one thing that you should understand, neural networks can definitely learn wrong, okay? There is always possibilities that they do. And the more things you have in the middle layer, in relation to the number of input data, might actually, render that result. So
the end result and decide if it is too much.
Exactly, exactly, and you really quickly get lost in changing the number of iterations, changing the number of learning rate. I upped the iterations from 40,000 to 60,000, which was great because I could see that now it was more clear that it detected the slow ascent and so on and so on. But the problem then is, so what happens if I have a slow ascent, but there is one bump? Is that then a slow ascent still? Or should I then say that this is a hard ascent? Or should I just learn the network that this is a slow ascent with a bump? You quickly get tangled into maybe the wrong things on what you're doing. Is that okay?
I have one.
You have one, yes.
Somewhere below you activate it by calling an activation function. Somewhere, if you go a little bit below, I saw you activate this training set, but I would just want to ask what is the activation function there, because I think there's a GS file that calls and the code from somewhere. So what kind of activation function does it use to store data? Is it like a sigmoid function, or is it like a relative function?
The activation here is just like I take the vector and I put it in the top of the neural networks, and I tell the network to evaluate this input, just like when you try to train it.
Yeah, but when it evaluates, does it like classify as this data is 1 or 0, or does it classify in a different way? Because there's an input and there's an output.
Sure.
That output is classified maybe.
Yeah, in the output in the training set I said that I wanted to, a non-ascent is 0 and a ascent is 1. So I've defined that there, that I want a number between 0 and 1 of the output values. Then the input values in this case can be different. I mean, I could use minus, I could use high values or slow values. So yeah, Elke. First Elke.
So thinking like if you want this to work properly, you need a model that can detect all these things that you want to detect.
Yes.
And so then you will probably need a lot of training data, right?
A lot of
training data.
Exactly. Yes.
And then it needs to be classified as well, right?
Yes.
So it needs to be so that you can do supervised learning.
Yes. Yes.
Yeah, so how do you think you could like scale that? Like how can you make sure that you end up with enough of this data? I mean, it's obvious you can get the data by just turning on the tracker.
Yeah,
to make it supervised, you also need to have like, oh, here I'm doing an ascent, so that you can then sort of teach the network to find the right pattern.
The only answer I have on that today is that inspect and adapt. This is how I do this, and I try to keep it simple. I failed a couple of times, maybe 3 times, where I tried to create a lot of data, and you really quickly get into the question, is this data clear enough or good enough as a reference, or should it be clear enough as a reference? I mean, you can discuss that forever. So the only answer I have on that is that keep it simple and you know, not too many, one middle layer. As you can see in the beginning, I started with just one slow ascent and one that was 0, and then I evolved from there. And obviously what then happens is that I had to bring in more data. So I had to maybe detect the slow descent, and I had to export that and put it in there and parse it and then train that vector, and then I had to have the other one.
Could you also, I don't know so much about it, but like, could you also make that unsupervised so that it's like just assigns a category so that you actually don't need to provide this?
That would be a different approach, which I haven't tested yet. That usually also requires more middle layers, a deeper network, and much more data. So much more time. Okay. Yep. Last question, maybe.
I was wondering myself, like that. This is a unidirectional layered network.
Yeah. Simple.
If you're using back propagation.
Yes.
Do you consider that algorithms? Other training algorithms?
Yes, there are lots of things you can do with the library, if that's your question. It's very versatile, and the new training set that I'm doing compared to the old way that I was doing a year ago is much faster, for instance. But I would say Google it. That's very easy to find, the different things you can do with it. I'm trying to keep the theory out of here and just be practical, but there's a lot of things you can do with it.
So the library is organized towards...
Yeah, you can find it.
No more questions?
Still in the middle of an answer.
Yeah, still in the middle. Okay, sorry.
I'll check the library.
I just want to start the first page because it kind of gives you an idea what you can do. This is a web application of some creatures that are running around, and you can't really see it, but there are small tracks here everywhere. And this is adapting to the fact that where it has been to where it has not been. So it's trying to cover the whole area, and they are keeping together, and they are trying to move around in a way that actually eventually covers every pixel of the area. It's small gray here in the background, you can hardly see it. And there are other things you can do, like painting a picture, for instance, recognizing images and stuff like that. So it's powerful. The reason I like this one is just the same reason as Elke described yesterday. It's very simple, it's very quickly to install, it's very fast to do something that actually amazes you. And I think that's again the passion that I feel when I'm working with this. It's always fun. I think that's enough. Okay?